Now that I've discussed the idea of a linear operator, we want to define the adjoint of an operator. So let A be an operator. So its adjoint, which is also called the Hermitian adjoint, of A is given by A dagger. And it's defined in the following way. If I take two wave functions, psi and phi, and I apply the operator A on phi and take the inner product, and if I then take its complex conjugate, then we get a number, a complex number. Now we can find another operator, which I called A dagger. If that acting on psi with taking the inner product with phi satisfies this relationship, then we call A dagger the adjoint of A. So this is the adjoint of A. This is the definition. So this is a definition. So in quantum mechanics, a certain class of operators play a central role. These are operators which are self-adjoint. So these are operators which satisfy the following condition. It means that if I have an operator which say, if I by the way, when we are defining the adjoint, this relationship means that the wave functions psi and phi are arbitrary. So this is for all a wave function. So an operator is called a self-adjoint operator if for all wave functions phi and psi, this inner product is given by this inner product, meaning that it doesn't matter if it's the operator itself or its adjoint here. If the operator and their adjoint satisfy this relationship for all wave functions phi and psi, then we call that operator self-adjoint. This is also sometimes called a Hermitian operator. So let us look at the consequence of the self-adjoint condition. So on the left-hand side, we know from from this definition of self-adjoint that we can write this as psi A phi star. And on the right hand side, we have phi A psi. But we know that when we take a complex conjugate of an inner product, it reverses the ordering of the wave functions in the inner product. So we can write the left-hand side as so if an operator is adjoint, then we can write it we can use this very useful relationship. So that means that A, if it's self-adjoint, then A can be acting on this or A can be acting on this. It doesn't matter. It gives me the same inner product. So next we want to discuss the eigenvalues of self-adjoint or Hermitian operators. So what are eigenvalues? So, when an operator acts on a wave function, we saw that in general it gives you some other wave function. But there are certain wave functions which, if you apply the operator, then you get back the same wave function. When we have where A is some complex number. So this equation is called the eigenvalue equation. And the number A is called an eigenvalue of the operator A, and psi is called an eigenfunction belonging to the eigenvalue A. So suppose that we have a spectrum of eigenvalues of A. So we have A, and we have a bunch of eigenvalues which I will label by some integer n, and it could be a continuous label as well. Then the eigenfunction which belongs to the eigenvalue an will be denoted by psi n, and then the eigenvalue equation would be A, the operator acting on psi n, giving me an psi n. So this is an eigenvalue equation. It's the same equation, but now I have labeled the eigenvalues separately, differently. So now we come to a very important postulate of quantum mechanics. And the postulate is the following. Let me make sure that we emphasize this postulate. The postulate is that every observable in quantum mechanics is represented by a self-adjoint operator. And if we make a measurement of that observable, then the result of that measurement will be one of the possible eigenvalues of that operator. So eigenvalues of self-adjoint operators play a central role in quantum mechanics.